All right, we'll go from current slide. So when you click on that, the first class that we had, I went over the syllabus, I went over my locator card that's when I'm in class, when I'm not in class, when I'm on campus, when I'm not in campus, and that type of thing. What time I come to campus, leave campus, all those things. And then we talked about safety, fire, weather, and active shooter type stuff. And then we talked about how the course would go. And then we started in Chapter 5. And then we finished Chapter 5 last time, and that's why I gave you the test on that today. So here's Chapter 8, Work and Energy. Okay? Now, I don't know if you ever think of work and energy as being the same thing, but in reality, they really are, or at least very closely related. And again, these are terrible, terrible PowerPoints. I hope I can find some lecture PowerPoints. This one that they show here is over on page 204, about 6 pages into the chapter. Okay, so let's talk about work first. 8.1 is work, and the first question there says, what is work? Anyone want to make a guess or tell me what your perception of work is? None? All right. Here is an example. I don't know how many have books. I see a few. Here we have a guy pushing on a crate. And I did some of this stuff before. I just don't have anything. Let's say I'm pushing on this table here. Okay? Now I'm exerting a force on the table. I'm really pushing. Am I doing any work? No. Why not? It's not moving. So here's a dumb example I gave. I think I may have introduced it last time. When my wife and I were, this was many years ago, looking for a different house. We had been living in a 2-bedroom bungalow, 2-bedroom, 1 bath, and we had lots of family and friends coming through town and staying, and it was fun, but it was pretty crowded when they did. So we had both gotten, she had started out as grad student and then a postdoc, grad student making almost no money and postdoc making a little bit more, but not a whole lot more. And I was working at, first at UAB as a programmer, making okay, but not great. And then got a job at Southern Research, which was made a pretty good increase. But then, so anyway, we were a little bit better off than we had been. So we were looking for a little bit bigger house so we could entertain more guests and family when they were coming through, because this is sort of a crossroad. And we were looking at this house, and I think I told you it had been built on a hill, but the part where the house was built was fairly flat. But some previous owner had built into the back of it, the house, and built into the hillside. So the water was coming down the hill. I mean, when it rained, it would come down the hill and just go against the house. And I was concerned about that hydraulic pressure on that new wall, the back wall that was built there. And also they had soil right up to the windowsill. And you do not want in the South soil to wood contact because of termites. Now they use treated lumber, I'm sure, and that will work for a few years, but after a while the treatment leaches out and the termites come in. So you don't want to have that. So I told my wife, we really need to do something to move the water and get the soil down away from the house. And she said, good, I wanted a patio anyway. Not exactly the job I had in mind, but I started that summer after we moved in. It was the first summer I worked at what was then Bessemer State Technical College, and we were, I only had a half load not even half a load that summer, teaching 2 5-week mini-term courses to the automotive students there, automotive math, and the rest of the summer I had off. So I had, basically a month or two, close to 2 months off. So we decided to dig out the patio in that time. And along about halfway, or maybe a little bit more, about halfway, digging the patio with a pick, shovel, and wheelbarrow, ran into this monstrous rock, okay? And I dug around it and dug and dug, and it just was huge. I call it a boulder, okay? And I thought I was near the base of it, and I struggled and struggled and pushed and pulled, sweated and spoke to it, and generally could not budge it. Was I doing any work? No, because I was not moving the rock. I felt like I was doing work. I would have said, I'm working hard at it, dear, but it wasn't moving. So technically, in the physics sense, I was doing no work. So if I'm pushing on the table and it's not moving, no matter how hard I push, how much I sweat, whatever, I'm not doing any work. Okay? Now this one, I don't know if y'all watch these things. I've only seen part of one, and that was enough for me. But these cheerleading shows or things like that, where these teams are competing against each other, it's always really dramatic. But when the cheerleaders are building these pyramids, okay, of people, those poor big guys or gals at the base holding up the rest of them, are they doing any work? They did work getting them up there, but standing there holding them, nah, nothing's moving, not doing work. Tell them that. You will not have happy campers. Okay, so what work is, whoops, that's not the pen I use. Here is the one, is, and here is the physics definition of it. Okay, work is equal to force, and this is the first book I've ever used that calls it displacement, is S, which is okay. There's nothing wrong with that, but that's force times the magnitude of the displacement. Okay? Work is equal to force times the magnitude of the displacement. Okay? Now, that's as long as the displacement is in the same direction of the force. Okay? If it's not, you're not doing any work. Okay? Here's a sort of a dumb example of that, but a true one. Would you say that the sun is exerting any force on the earth? No? Okay? If I had said, is it doing any work on the earth, no would have been a good answer. Okay? But is it exerting a force on the earth? Of course it is. The sun is the center of our solar system. The gravitational force of the sun, and by the way, we talked about gravitational force on the earth. Gravitational force on the sun is hugely bigger than that of the earth. So yes, it's pulling in on the earth all the time, but the earth is moving perpendicular to that. So the force is this way, the motion is that way, no work is being done there either. Okay? So work, the answer was no in general, but the force, yes, for sure there's a force on it. That force creates a change of direction. It doesn't create a change of velocity at all, okay? And that's what work is. So work is force times displacement as long as the force is in the same line with the displacement, okay? And they say here magnitude of displacement. Since we're not going to get into, we talk about vectors some, but this book doesn't really talk about them a lot, and I'll mention them some, but vectors have two ways, really kind of like three ways you can multiply them, but since you haven't had any vector algebra or anything else coming in, I'll just sort of ignore that, but that's, you can talk about it because force and displacement are vectors. This is a dot product, which means you're just multiplying magnitudes and times the cosine of the angle in between, And the cosine of 0 is, does anyone know that? Y'all haven't had trig either. 1. So nothing changes there. But cosine of 90 degrees is 0. So that's why the sun does no work on the earth. It changes the direction of the earth's motion, but it doesn't do any work on the earth, on the motion of the earth. Okay. Now, what are the units then for work? What is our primary unit for force? You can use either system you want to. What's our basic unit for force? Okay, Newton in the SI system, that System International, we sometimes call it metric, or pound in the U.S. customary system. What is displacement? What would you measure displacement in?
Meter or feet.
Second?
Would it be meter or feet?
Yes, that would be meter in the SI unit and feet in the U.S. customary. So most of the time we'll say it the other way. Well, in U.S. customary, we'll call it foot-pounds. Okay? You probably have heard the term before, foot-pounds. Here, a Newton meter is a Newton meter, but it has its own name. I don't know if the book mentions it yet. It doesn't, but I'll go on and tell you what it is. A Newton meter is the same as a joule. Now, that's capital J. And by the way, I did tell you before why they capitalize some units. Did I tell you that?
I don't remember.
They name them after people. So Newton's named after Sir Isaac, so it's a capital N. Joule is named after James Prescott Joule, who did a lot of the early work with mechanical equivalent of heat and those kind of things. So a lot of early work with work and energy. So they named it after him. And that, by the way, his name is Joule, not Joule like, you know, a valued piece of rock. Not that kind of Joule. Okay. Is it Camry? Huh?
Cameron, right?
Camry, okay. I thought it was. I keep wanting to call you Camari because, but it's Camry, right? Okay, is that right? Camry, okay. That's what I thought. So all we're missing that I know of is Jeremiah right now. And because you just came in, I got a present for you. Okay? This is test objectify. And it's take home. You have at least a week to work on it. If you need more than a week, you can have it, but you know, try to get it done in a week. But if you finish it earlier, you can turn it in next time, you know, or whenever you finish. Okay? So we're talking about work. Work is a force times a displacement as long as they're in the same direction. The units for a Newton meter in the SI units, which is a joule, and foot-pounds in the U.S. customary unit. Now, I got rid of my book. I didn't mean to. Okay. And if you have your book, you see the little blurb on James Prescott Joule, upper right corner of page 203, and you can read that. He was an interesting character. This doesn't go into a great deal about him, but he was a commoner, okay? Back then, usually, and this is 1843 to 1878, when he did most of his work in England. And back then, the people who were generally the best educated were the landed aristocracy, you know, the lords, the ladies, the knights, these kind of people. And the common folks generally didn't have opportunity for a good education. He did, because about this time, the middle class started growing in England. And his father was a brewer. I think he brewed beer, if I'm not mistaken. And so therefore he started making some bucks, okay? And with making money, then he could afford to educate his children. But he still wasn't considered upper crust. Even though they were wealthy, relatively speaking, he still wasn't considered on the in crowd. So generally people, they were considered commoners. Well, James Prescott Joule, I don't know if it was diagnosed this way, but the evidence seems to be that he may have been hemophiliac. So therefore he couldn't do manual work like most other people, because if he ever got a scratch, he might bleed to death, or, be a pretty tough situation there. So he basically studied, and he had a brilliant mind, and did lots of experiments, but the elite of the scientists were this upper crust crowd, the Royal Academy. You almost had to be royalty or recognized by royalty to be in it. Well, there was a guy who was surprisingly a great scientist in the upper crust guy. He was actually a lord. His name was William Thomson, but he was Lord Kelvin. That was his title. And Lord Kelvin recognized the incredible work that James Prescott Joule was doing, and he took him under his wing, brought him into the Royal Academy and said, look, guys, I don't care if he's not royalty like you are, this guy's smart, okay, and he's contributing big time. We're going to admit him. And they did. Lord Kelvin did a lot of the compilation of what we can now call thermodynamics, okay, and he brought him in, and they worked together on several things. So, by the way, the absolute temperature scale, anyone know what it's called? The Kelvin scale, after Lord Kelvin. We have Fahrenheit, we use in U.S. customary. Celsius, they usually use in most other countries, but the absolute scale, the SI scale, is Kelvin, named after Lord Kelvin, not named after William Thomson, named after him, but his title rather than his actual name. So it's still capital K. So here's example 1 on page 203. Find the amount of work, and this figure has nothing to do with it, the amount of work done by a worker lifting 225 newtons. Okay, what is that? Newton measures, second, force or weight. A weight of 250 newtons of bricks, okay, not a meager, a mild thing here, to a height of 1.75 meters. Now that's pretty reasonable, because I'm right at 6 feet, which is right at 2 yards, and a meter is just a little bit more than a yard. So if I lifted those bricks, I'm glad I don't have to, up, and say the picture in the book has it somewhere about here, somewhere here. This is about 1 meter, and this would be, what did they say, 175? Yeah, he has it up on his shoulder. So that would be about like the picture indicated in the book, about 1.75 meters. So he lifted them from the floor up to 1.75 meters. How much work did he do lifting them? Okay. Yeah, he was reading the book, right? Okay. Oh, you already done the math. So the work is equal to force, which is 225 newtons, times the displacement, which is 1.7, well, I should put S, okay? And this would be 225 newtons times 1.75 meters, and that would be, what you say the number was?
393.75.
393.75, you said? And what units? Never just give me a... By the way, for those who weren't here in class to hear me harp about it, numbers by themselves are fairly meaningless. They're nice, they're numbers. You always need to follow them with a unit. So 373.75 joules, Newton meters or joules. Either one of those is acceptable. Now, on this, because you have 3 significant digits here, 3 significant digits there, I would definitely round this to be 394 joules. Okay? Now, that's because you can't get more precision out of a problem than you put in the problem. The number of significant digits indicates how precise your measurements are. So you can't get 5 digits out when you only had 3 digits coming in. So, again, not a huge deal, and that's why they called it in the book 394 Newton meters or 394 joules. Okay? Now, example 2. All right for me to erase this one? Okay? You got it? Okay. A worker pushes a 350-pound cart. So that's a 350-pound cart. What's that a measure of? Force or weight, either one. Okay, because weight is a force. A distance of 30 feet. And they put a line over the 0, which indicates what? That's a significant digit. The 0 is significant there. Okay? And that would be your what? Displacement, which I usually call D. The book is calling it S, so I'll put it in as S. Okay? Exerting a constant force of 40 pounds as shown in the figure. So he's pushing with a constant force. So this, I'm going to go back and correct this, okay, because we have 2 forces here. I'm going to call, well, I'm going to go back and do it like they did. The force due to, what did they call it, for the G or W? It's the weight force. And I can't remember. Some books call it F sub G and some calls it F sub S. I mean F sub G or F sub W for weight. I'm going to call it F sub G. That's the weight. Little w, D, W, weight. By the way, capital W, little w stands for weight. Capital W stands for work. Too many words starting with W, so that's how we, on the parameters, that's how we refer to those. So that's your weight. Now, he's pushing the cart with a constant 40 pounds of force. So this is the, I'm going to call it the applied force. Okay? Just because it has 350 pounds of block on it, or whatever it is, looks like block, he's not lifting it. Okay? He is pushing it, rolling, you know. So the weight of it really doesn't matter too much. He's having to push with a constant force of 40 pounds. That's in the same direction of the displacement. The weight, which way is weight pushing, pointing? Yes, toward the center of the earth. So the fact that he's moving it this way, it's moving that way, the force is that way, that's the one that we use for how much work he's doing. The force downward when he's pushing it that way doesn't matter. Again, that's perpendicular force to the displacement. It doesn't matter. So the question is, how much work did the person do? This is almost immaterial here. Here's what we use. The work is applied force times the displacement, which is what? 40, with that 0 being significant, pounds times 30 feet, with that 0 being significant. And what does that come up being? Second? 1,200, and we usually reverse the order and call it foot-pounds. Okay. And there's Jeremiah. Okay. There we go. All right, we got everybody here that we've had so far. We're now up to 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. We got double digits. 4 and 6. Okay. Technically, they don't like for us to run courses with fewer than 10. Now, I'm hoping all of you are paid or in the process of paying, right? Okay, good deal. Because they really want 10 paying students, so please get that taken care of. Because they're just initiating this program, I didn't have much worry about them when we started, what, we have 7 here? Something like that. I thought, yeah, they're still going to run it because they're trying to build this program. So now that we got 10, I feel much better about it. Okay. So, which of these zeros are significant, or both of them? Or neither of them? Huh?
They're both significant, right?
The what? No. Only the 1, 2 are significant. 2 digits, 2 digits, 2 digits. These are not significant. So you do not put the bar over it. Not that you probably would put the bar anyway, but the work done by the guy is the force in the direction of displacement times the amount of displacement. So that's 1,200 foot-pounds. And they don't put the bar over either of those zeros because the 1, 2 are the 2 digits that are significant. All right. Now, even though the cart with all of its block on it, was there a question? Oh, I'm sorry. By the way, I'm hard of hearing. That's why I talk so loud. I don't think I'm talking loud, but my wife said, yeah, you're talking loud. Okay, so yeah, you have to speak up. Yeah.
Yeah, what do you mean by significant?
Okay. Okay. When you're, okay, let's just talk a little bit about here's an example. If you had taken that, and this was not this problem, but if you had taken that 40 and been dividing by 30, what did your calculator give you? Someone do it. 40 divided by 30. What do you get? 1.3333333333333333. As far as it goes. And I've had students that give me that as an answer because that's what the calculator told them. Well, obviously, you don't have that kind of precision. Your calculator may have, what, 8 or 10 digits on it. If you only had 2 digits going in and 2 digits going in, you can't give me 9 digits precision coming out. What significance digits are mean how many digits really matter. Okay? Let's see. No, I've already erased it. On that previous one, when we calculated 393.75 joules, that was what your calculator gave you, right? That's 5 digits of precision. You only had 3 digits coming in, 225 newtons, 1.75 meters, only 3 digits coming in. You can't give me precise answers to 5 digits going out. That's what we mean by significant. The number of digits that are meaningful. That's why count the first 3 digits, because you had 3 coming in from both sources. Look at the next one over. It's a 7. It's greater than 5, so then you bump up 394. Okay? And forget about the other digits. They just aren't significant. You cannot get more precision out of a problem than you did going in. It's kind of like, I'm trying to think of something that might make sense to you.
It's making sense.
What's that?
It's making sense.
It is? Okay. All right. All right. Okay. So that's why you had 2 digits coming in here, 2 digits coming in there, so only these 2 digits are significant. The last 2 zeros are just placeholders. They've got to be there, but they're not significant digits. Okay. Now, their comment here that even though the cart weighed 350 pounds, but he only was pushing on it with a force of 40 pounds. That was the force in the direction of the motion. The 350 pounds was toward the floor. That is being, remember we talked about equal and opposite forces, Newton's third law of forces. The floor is pushing up with the cart with 350 pounds. So those aren't contributing to anything. Now if he was lifting the cart, yes, then he's having to overcome that because lifting is in the same direction of the force due to gravity. But he's not lifting the cart. He's pushing it perpendicular to that. Now, here's another thing. Let's say he was pushing the cart down the slope here. Or pushing the cart up the slope. Okay? Same cart, same wheels, same friction, same everything. Which is easier? Pushing it up the hill or down the hill? Down, because there gravity is helping you. You're not having to do that part of the work. Gravity is pulling down a little bit with you. Whereas this, you're having to push on the cart plus push against gravity. You have two components of force there. So that would end. High quality. Stand here. That's why I don't use it. Okay. So then you would have components of forces, which is what we're going to get to very soon, as in the very next thing here. All right. So recall that the definition of work states that the work is the product of the force in the direction of the motion and the magnitude of the displacement. They have to be in the same direction. Now, it could be stated this way: the force times the motion in the component in the direction of the force. You could say it either way. Usually we say magnitude of the force in the direction of the motion. That makes a little more sense. Okay. And sure enough, they are going to get to a little bit of trig here. Now, I'm guessing that y'all haven't had trig, or have you? You have had trig? Everybody, or some haven't? Okay. Long time ago. Let me give you a few of the characteristics of trigonometry, all that you'll need probably in this course. Okay. And here's the example that we have here. I'm going to get rid of this writing because that has nothing to do with this example. Okay. Here, we're dragging this box. Let's say we have a string tied to it or something like this, and we're dragging the box across the floor. Okay? When we're dragging the box, we're exerting a force on the string, right? Okay? Now, part of that force is an upward force, and part is a lateral force. Which way is the box moving? The crate. It's dragging across the floor. It's not moving up at all. So this component of the force is not contributing anything to work. It's perpendicular force, okay? Only the component in that direction. So we're concerned with this, what we call F sub x. Usually we have x, y, okay? Vertical is y and horizontal is x. So that's why we call it F sub x. That's the only component of that force, the red force, that's contributing. Okay. Now, notice that makes a nice little right triangle. Now, what do we mean by right triangle? Say again? Yeah, one of the angles is a 90 degree. Okay? So we have, and if we were concerned with it, which we're not, we would call this F sub y. That's the component of the force upward. Okay? We're not concerned with that now. It's not contributing to work at all. Okay? But that would be your F sub y. The F here is the force that's opposite the 90 degree angle. Now, someone tell me, what's the sum of the three angles in any triangle? Anyone know? Sum of the three angles in any triangle. 180 degrees. You're absolutely right. Okay? Now, if it's a right triangle, meaning one of those angles is a 90 degree angle, you've already told me that. Why do they call it right, by the way? The Greeks were under the impression that the right angle was the perfect angle. And it really does make sense. Okay? Let's imagine that when they were building this building, they thought it would be neat to have the wall leaning out or leaning in. Good idea? No, because the upper story is pushing down on that. The greatest strength comes when it's perpendicular, when it's coming down at a right angle. All the force up there is coming straight down here, not trying to fall inward or outward, okay? When I was growing up on the farm, we tried to stack the hay perpendicular, okay? You don't try to lean it one way or another. If you're leaning it this way, it's going to fall. Over time, it's going to fall, okay? So, that's why they called them right angles, okay? Because it was a perfect angle, the right angle to use. Okay, so we call this setup here. This is the angle theta that we're interested in. That's between the horizontal and the applied force. So that's the angle of interest. Now, there's three sides of this triangle. Okay? The side opposite the 90 degree, and this is a right triangle, side opposite 90 degree, let me get back to this. 180 is the total. If this side is 90, what's the sum of the other two angles? No. Yeah, the sum is 90 because 90 plus 90 is 180, right? So guess what? Neither one of those, both of those angles are less than 90. The only way they could be 90 is one of them 0, and then you don't have a triangle. You have a straight line, okay? So that's not a triangle. So both of those angles have to be less than 90. We call those acute angles, okay? Aren't they cute? No, never. Acute angles, okay? And because they add to 90, they're called complementary angles. Aren't you cute? Yeah, that's complement. No, it's complementary. It means complete. Those two angles add to make a right angle, a complete angle. So they're complementary to each other. So those are just little things. Okay? So this angle theta we know is less than 90. It's an acute angle. Okay, and if that's the angle we're interested in, then the side opposite the big angle, the largest angle, 90 degrees, is called the, anyone know what you call it? Hypotenuse. Ever hear of that? Okay, the hypotenuse. It's the side opposite a right angle in a right triangle. Always the hypotenuse. A Greek word, obviously. Okay? We don't use words like that anymore. Okay. Now, the other two sides we give these names to. If this is the angle of interest, theta, they usually name angles, by the way, from the Greek alphabet. Okay? So if that angle theta, the side opposite that, we call the opposite side. Okay? That's not a 0, that's an O. The side adjacent to that is called the adjacent side. Pretty clever, huh? A lot of times they would do OPP for opposite and ADJ for adjacent. I'm just lazy. I'm just going to call it O and A. Okay? Now, based on that and right triangles, there are certain features, characteristics that are always true. And here's what they are. You have 6 trig functions. The first of these is called the sine. Now, it looks like sin, but that's the first 3 letters. Actually, if you write out the word, it's S-I-N-E. So they just use the first 3 letters, and that's the sine. The sine of any angle theta is the opposite side over the hypotenuse. Okay? The cosine, it's C-O-S-I-N-E, just use the first 3 letters of that angle theta, is the adjacent over the hypotenuse. And the tangent of that angle, theta, is the opposite over adjacent. Now, those are the only 3 of the 6 trig functions you're really going to use, I think. If we ever need cotangent, secant, or cosecant, we'll deal with them. I don't think we'll need them. Those 3 are going to handle us here. Now, if you need a little mnemonic help for this, remembering what those angles are defined as, and it makes sense. This is the side opposite that angle. This is the side adjacent to the angle. Now, the hypotenuse is also adjacent, but it's the long side. So that's the hypotenuse. Okay? Now, I had a roommate. He was an undergraduate when I was a grad student in at University of Nebraska-Lincoln. And he used this to help remember it because he was taking trig his junior or senior year. He said, sa, ka, toa. And frankly, sa and ka sound so similar to me, I don't find that's very helpful. But he thought that was really helpful. Sine is opposite over hypotenuse, cosine is adjacent over hypotenuse, and tangent is opposite over adjacent. But then when I started teaching at Western State Technical College, which is now the Western campus of Austin State Community College, probably in the first year or two that I was teaching, I taught my first trig class there. And I was teaching it, and some gal in the class said, "Oh, some old hag caught another hag taking oats away." I'd never heard of that before. I like that a lot better than Sakatoa because I have to stop and say, well, sine is opposite over adjacent, so that sa, cosine is, I have to know what it is to know which one to use. But some old hag caught another hag taking oats away. Ha! That makes perfect sense, and it did. I just don't like the term hag. Well, then another term or two, next time or a time or two later when I was teaching, another gal said, no, I learned it. Some old hen caught another hen taking oats away. I like hens a lot better than hags. So I'll call it some old hen caught another hen taking oats away. And that's how you can remember these. Okay? So what we know here is that what is the trig relationship that relates the hypotenuse with the adjacent? Hypotenuse and adjacent? See, you know this force, that's what you're pulling. You need to know the horizontal component of the force. That's the adjacent. So what trig function relates adjacent and hypotenuse? Caught another hen, right? So that's cosine theta is equal to the adjacent side, another, that's f sub x. That's what we're looking for over f. That's your hypotenuse, right? And then you multiply both sides of that by f, because we're looking for this f sub x, by f, and there you have f sub x is equal to the total force times the cosine of the angle in between. And that's what we'll use. And we're going to use it many different ways. And occasionally we'll be using sine, if you're interested in what that y component was. Right now we're not. But if you were, we would use sine for that component. Okay? And sometimes we're not really interested in the hypotenuse at all, but we're interested in the ratio of the vertical to horizontal or vice versa, and then we'll use tangent for that one. Okay? Taking oats away. All right. Does that make sense? Now, so that's where we get the work done is equal to the x component of force times the displacement, which will then be the force you exerted, the applied force, times, well, let's go on and put the displacement, times the cosine of the angle in between. And that's where they get the formula there. Let me clean that up a little bit because it's kind of ugly. Okay. Fs times the cosine of the angle in between. Does that make sense? So there's the formula we'll use most of the time because we're dealing with the horizontal component. That's what we're doing. That's f times the cosine of theta. But we usually will know the force. How much are you pulling? Okay? We don't know what that horizontal component is, but this will give it to us. Now let's just do a couple of things about sines and cosines. Because your hypotenuse is always the longest side. Always. Never equal, always longest. So your opposite and your adjacent have got to be smaller, right? So therefore, the sines and the cosines are always going to have values between 0 and 1. Right? Now later, maybe we'll have circumstances we'll deal with negative angles, but it'll always be between -1 and 1. Never outside that. So expect that. So when you multiply Fs times the cosine theta, you know that whatever F times S is, the cosine theta is going to reduce it a little bit because you're multiplying by something between 0 and 1. Okay? Now, the book does this. This one down here, they put absolute values on them. Now what that means is the magnitude of those forces. And yeah, if that happened to be a negative force, we're not interested in negatives. We want absolute value or magnitude. Magnitude is always positive. The hypotenuse, by the way, is always positive. No matter which way it's pointing, hypotenuse is always positive. So we technically use absolute value or magnitude there. Okay. So we're ready for example 3. Let's see if they have. Here's example 3 right here, I think. A person pulls a sled along level ground. So this is level ground here. This line here, level ground. A distance of 15.0 meters. So you say is pulling it from somewhere back here to somewhere here, and this is 15.0 meters. That means significant to 3 decimal places, meaning it's to the nearest tenth of a meter, not just 15, a little more than less than 15 and a half or a little more than 14 and a half. No, this is good to the tenth of a decimal place. That's what we mean significant digits. That 0 is significant. You don't need a bar over that one because it follows the decimal sign. Okay, decimal point. Okay? By exerting a constant force of 215 newtons at the angle. So here's this constant force here. That green arrow represents the force. Remember, forces are vectors, magnitude and direction. There's its magnitude, its direction is at an angle of 30 degrees with the horizontal, with the ground. So there's your 30. Notice this is 3 significant digits, and you have measured, he has that thing exactly 30.0 degrees. That's not very likely, but with the ground. How much work does she do? It's not a he, that's a she, okay? How much work does she do? How would you calculate it? What is work? Force times displacement. Okay? Now that's force in the direction of the displacement. This force is not in the direction of the displacement. It's sliding along the ground. There's the displacement. This is it right here. There's your 15 meters. That's horizontal. This force is at an angle. So you can't use that force times that displacement. So what do we use instead? You want this component of the force here. This is your F sub x. That's in the same direction as your displacement. It's supposed to be a straight line, by the way. It's not. How do we get F sub s? F sub x. What was that? Just did it before. F sub x is equal to the force times the cosine of the angle. So this will be this is the F sub x is what we need there. We weren't given F sub x, so we calculate F sub x to be F times the cosine of 30 degrees. Okay? And that F is your 215 newtons times your displacement of 15.0 meters. I should have put it. So this will be the work done is the 215 newtons. That's the applied force and that's newtons, times, and let's go on and put the 15.0 meters, times the cosine of the angle in between, 30.0 degrees. Now, if you have a calculator, all you have to do is plug it in, if it's a scientific calculator or more expensive. If you have a little cheapie, you know, those little giveaways and things like that, they're not going to have sines and cosines on them. And it looks like to me you probably are going to need it, so I would definitely have a calculator that had sines and cosines on it. Now, for these common angles like this, I'm going to give you another little mnemonic device. Okay, we're going to take the first quadrant. Here the sine is 0. Or, I mean, the angle is 0. Horizontally, that angle would be 0. That's 0. That's 0. I can't write. This up here is 90 degrees. Okay? This one that splits the difference is 45 degrees, half of 90, right? Then you have another angle here that's a third of 90. Okay? And that would be 30 degrees here, and that would be 60 degrees there, leaving you 30 here. Okay, right? Now, these are our favorite little angles. Okay? Not all your problems will have this, but a lot of them will. I'm going to give you the opposite values. Those would be related to the sines of these. This one's the square root of 0 over 2. Well, why do I write it that way? You'll see in a minute. It's square root of 0 is 0. 0 over 2 is 0. The sine of 0, the opposite side here is 0. Yeah, you don't have any opposite side there. All your force is horizontal. Okay? This y value here, this height here, is the square root of 1 over 2. What's the square root of 1? 1. So that's 1/2. Okay? The 45 just happens to be the square root of 2 over 2. And that's indeed what it is. And the 60, that's the square root of 3 over 2. And then the 90 is the square root of 4 over 2. What's the square root of 4? 2. And 2 over 2 is 1. Okay. So these work for these simple little angles. 30, 45, and 60. It's square root of 1 over 2, square root of 2 over 2, and square root of 3 over 2. Okay. But we're interested, that's for the sines. The cosines go the other way. Cosine of 90 degrees is 0. Cosine of 60 degrees is, this is square root of 0 over 2. This is square root of 1 over 2. 45 is again square root of 2 over 2, which makes sense because 45 is especially halfway. The x and y have to be the same. And then the 30 would be the square root of 3 over 2. And cosine of 0 degrees is square root of 4 over 2, which is 1. Okay. Cosine of 90 degrees is 1. Okay? So those are maybe helpful little things. So that 60 degrees is 1/2. So this will be cosine of 30. I'm sorry, I said it backward. Cosine of 30, then the adjacent side will be square root of 3 over 2. Now that's probably not very helpful to you either. But even the little cheapy calculators, most of them have square root signs on them. So even if that's all the calculator you got, you can do that using that. So this will be, if someone's got a calculator with a sign on it, do it. 215 times 15.0 times cosine of 30 degrees. Oh, and by the way, your calculators, if they do have the sines and cosines and tangents on them, it's important you get in the right mode. Because you could use radians or you could use degrees. If you're in radian mode and you type in 30, you're going to get a wacko answer. It'll be wrong. Okay? So you better get in degree mode. If you have a calculator, figure out how to get in degree mode. I'll try to help if I can. Are you using a telephone back there? A smartphone? If you are, there's a way to get in the right mode with that too. Usually it's some symbol that says degree to radian or radian to degree or something like that. So get in the right mode first. So it's 215 times 15.0, which you don't have to multiply that, times cosine of 30 degrees, which would be square root of 3 over 2. If you got a cheap calculator, you could do it that way. What does that come out being? Anybody? Second?
I got 2,792.90.
90 what?
2,792, but I don't think that's correct because it doesn't actually go.
Okay, because you have 3 digits here, 3 digits there, 3 digits there, so they probably are going around to 2,790. What unit? Is that not the answer? Yeah, that's the answer they got, yeah. And what units? Newton meter is either a Newton meter or a joule. Okay, that's the unit. Okay, why do we round? You only had 3 significant digits going in your force, in your displacement, and in your angle, so you can't get 4 significant digits coming out. You're limited to 3. So you take the first 3, you look, once you get the first 3, look to the right, the next one's less than 5, so you just round down. I mean, you just make it a 0. Okay? Yeah. All right, good deal. All right, to go to the next slide. Next example. Got it? Okay. Example 4. Juan and Sonia use a push mower to mow a lawn. Juan, who is taller, pushes at a constant force of 33.1 newtons on the handle at an angle of 55 degrees with the ground, whereas Sonia, who is shorter, pushes at a constant force of 23.2 newtons on the handle at an angle of 35.0 with the ground. Let's just see if, I doubt if they have, no, that's not Juan or Sonia. Okay, so let's draw a picture. By the way, folks, when you're working problems, good idea to draw pictures. Even if you're no more talented in drawing than I am, draw pictures. Pictures are worth thousands of words. Hopefully you'll see what's going on here. So here we have Juan. He's pushing on a lawnmower, so let's have Juan here. Well, let's see, his arms are like this, pushing on the lawnmower. This is really ugly, isn't it? Okay. Here's the lawnmower down here, mowing along. Okay. We'll put a head on Juan. Okay. Because he is taller, he pushes with a constant force, so his force downward here, there's his force, of 33.1 newtons. Okay? At an angle of 55 degrees. So Juan's angle is 55.0 degrees. The decimal place got buried there. Okay? With the ground. Sonia, who's a little bit shorter, okay, is pushing the same lawnmower, but at a lower angle. So here's the wheels, and here's the mower, and blah, blah, blah. Okay, so she's pushing. Because she's shorter, her angle, she doesn't like to work it. Well, she's not pushing as hard. Her force for Sonia is 23, I can't write, 0.2 newtons. So this is force due to Juan, and this is force due to Sonia. My J looks so much like an S. Let me see if I can make that look a little better. Okay. Okay. F sub J. It's a little bit better maybe. That's F sub S. Okay? And she makes an angle of 35.0 degrees, right? With the ground. Assuming they each push the mower 300 meters. So both of them are going to put, 3,000, I can't read. They're both going to push 3,000 meters. She's going to push 3,000 meters. Same length, okay? And by the way, the third zero, the middle zero, third place is significant. So everything is 3 significant digits. Who does more work and by how much? Well, one's force is greater. Wouldn't that mean he's doing more work? No, his angle is greater too, so that means he's pushing down with force that doesn't do any work. Only the horizontal component does work. So let's calculate the work done by 1. Work by 1 is what? Work by 1 is what? Okay. His force applied is times his distance times the cosine of the angle. Okay, so we'll plug it in. That's 33.1 newtons. That's his force. Times displacement was the same, 3,000 meters. Okay. Times the cosine of, what was his angle? 55 degrees. Okay. Anyone got a calculator that does cosines? See what you get. Everything has 3 significant digits. So give me rounded to 3 digits. Okay, as you can easily guess, the next test is going to have similar problems on them. So if you haven't secured a calculator by then, and telephones will work, smartphones will work too. You just need to know how to operate them. The one thing I've noticed about smartphones, usually calculators, not always, but usually calculators follow the rule of order of operations pretty well. As far as I can tell, smartphones may not always. So you have to be sort of careful with them. This is just straight multiplication, so you wouldn't have a problem. What do you get? Work done by 1 was, it's going to be a pretty good sized number. Close, not quite 100,000, but somewhere close to it. Say again? 67? 57? 57,000. One more digit.
Well, the number you get in the calculator is 56,956.
Oh, wait. 56,950 what? 6. Okay. And that would be joules. But these two aren't good. So you count off 3 digits. Oh, they pulled one on you here. The third digit is your 9. Look to the right. That's 5 or greater. So you're going to round up. So that does round to 5. The 9 rounds to a 10. The 10 makes the 6 go to a 7. So that would be 7,000 joules, with that 0 being significant. Because you see the 5 makes the 9 roll to a 10, but that 0 is significant. These other 2 are not. Make sense? Yeah, so you were right. I'm sorry. I was asking for, because I don't have a calculator up here, I wasn't doing it. So let's check on Sonia, okay? Her force, the work done by Sonia, is, her force is 23.2 newtons times 3,000 meters middle zero being significant, times the cosine of 35 degrees. Okay, what do you get when you plug those in?
57,012.
57,012, and that would be joules. Well, that also rounds to 57000. But she does do more work, a slight amount more, okay? And it says, assume that each person who does more work, Sonia by a little bit. And how much? When you subtract these two, 57,012, subtract from that 56,956, that would be 556 joules more. Not much, okay? Not much more, okay? She beats them by 56 joules. How did the book come out? They do the same amount of work, however, one must exert more energy because he pushes into the ground more than Sonia. So you see, you can't even say that. Those 56 joules are... have you ever seen a display, say, of your of sound quality, okay? And you get a lot of what they call noise, sometimes called white noise, buzzing in the background, that kind of stuff that's not contributing, okay? The 56 are in the noise. You can't see that. They did the same amount of work, even though he exerted more force than she did because he was pushing into the ground because he was at a steeper angle. She was pushing more, somewhat into the ground, but not nearly as much. So they did the same amount of work. Okay? So let's, all right, to erase this. Okay? And by the way, remember the screencast-o-matic doesn't just record the projection. Well, it does record the projection, but it doesn't just record the PowerPoint. It records what I'm saying, because there's a microphone in my computer, and what's being projected. But you see, what I'm writing on the screen is being projected too. Now, if I get up there and wave my arms, no, it doesn't pick up that. Okay, only what's being projected. So let's go to example 5. Find the amount of work done in vertically lifting a steel beam with a mass of 750 kilograms. Now, they just told you what that was. The symbol for mass is little m, 750 kilograms. Okay? Now, you folks that weren't here last time, remember or be aware, mass is not the same as force. Mass is not the same as weight. Mass is how much of an object is there. Force or weight is how it is responding to the gravitational field it's in. Okay? Find the amount of work done by vertically lifting a steel beam with a mass of 750 kilograms at a uniform speed, a distance of 45 meters. So the distance here, or we could call it S, is equal to 45 meters. And that, we assume, is upward. So you're lifting upward, and the displacement is upward. Okay, now, find the amount of work. What is work, folks? Force times displacement. Can I put D? I just like D better than S, okay? But what's your force here? What is the force here? No, it's not. That's the mass. What is force? Newton's second law? Second? It's what? Oh, I know it was 2 days ago. I mean, yeah, 2 days ago. A long time. Yeah. It's chapter 5. I'll go on and do it. The force here is also the weight. They sometimes, I can't remember what this book calls it, F sub G, force due to gravity. And that is mg. Mass times the acceleration due to gravity. Newton's second law, mass times acceleration is force, net force. This is the acceleration due to gravity. Now, we're in what units here? Kilograms and meters? What units? Kilograms and meters. What units are we in? Second? SI, yeah, I can't hear. That's what I said. Oh, okay. SI or metric either, that would work too. So what's our acceleration due to gravity in SI units? We have the mass, we need the G. And now here's an assumption, folks. Have to have this assumption in there. We're on the surface of the Earth. Is that a safe assumption? Yeah, we're not out on Mars or somewhere lifting this beam. We're on the surface of the Earth. So what is the acceleration due to gravity on the surface of the Earth? Anyway, 9.80 meters per second squared. That's it. So we first have to get the force, so we can put that in here. So the force is also your weight, and that is the mass, 750 kilograms. Now they should have, if they were being fair about it, they should have probably put the bar over the 750. I'm guessing no, they didn't, and I bet you it's on purpose. Because you see, this is only 2 digits. My guess, those are only 2 digits. They don't have the bar over it. So the really 9.80 isn't going to matter. We can still use it, but we're only going to get 2 digits here. Okay? So this times 9.80 meters per second squared. And that's going to be the force or the weight of, someone punch that in? Or we can just put it in here. Let's just put it in here. Let's do mgd, okay, or h or s or whatever you want to call it. So that's 750 kilograms, okay, times g was 9.80 meters per second squared, times your displacement was 45 meters, and that was no cosine here. Because you're lifting upward, the displacement's upward, the angle between that is 0. Cosine of 0 is 1. You don't need the cosine in here. So if someone's got the calculator, this is just a simple, even a cheapie will do this one. 750 times 9.80 times 45. What you get? Okay. I'm just going to do a quick calculation in my head. 750 times 9.8 is almost 7,500 times 45, which is a little less than 50. That would be around 14,000 something. What do you get? No. Say again? A little louder. 33? 075. That's a comma there, right? That would be units of what? What's a kilogram meter per second squared? What's another name for that? It's measuring a force, hint, hint. In SI units, hint, hint. Newton. Newton meter would be a joule. However, I can almost guarantee you that's not what the answer in the book is. Because here we have 2 digits. There we have 3, but who cares? Here we have 2. So we can only have 2 digits here. Look to the right. It's a 0. Change all those to 0. 33,000 joules. Okay? Now, is that what they get? Well, they say times 10 to the 5th. No. This must have been 330.
Yeah.
Oh, okay. Someone's trying to lead me astray here. Okay. Okay. What was it? 3. Wait. Okay.
Yeah.
Okay, say that again now. 75 what? 0? Okay. That would be joules. But we round because we only got 2 digits. Look to the right, 0. Make all those 33,000,000 joules. Okay. Only those 2 are significant. None of those zeros are. Okay. Now, the book expressed the answer slightly differently. Kind of get used to it. In scientific notation, you move the decimal 1, 2, 3, 4, 5 places, 3.3 times 10 to the 5th joules. Now, frankly, I like, that just takes so much room to write. Because we're in metric units, right? Let's just do those 3 there. And what would that make? 3 zeros means 1,000, right? And what's 1,000 in the prefix that means 1,000? What's 1,000 meters? Kilometer. So on the street they call them kilos. No, we don't call that. Oh, y'all are supposed to know that. Okay. That's 1,000 grams, by the way. Okay. Okay. But that KILO means 1,000. So I would have written this as 330 kilojoules. That to me is just a lot easier than 3.3 times 10 to the 5th joules. But the book likes scientific notation, so that's perfectly fine.
It does say that in the book.
Oh, they do? Oh, yeah, there it is. They do say that. You're right. That would also be an acceptable answer. Good for them. Okay. That finishes 8.1. Here we have problems 1 through 6. Remind me, the odds are in the back. Tell me something. Do you see a 5 anywhere in there? I see 1, 2, 4. No, I don't see a 3 either. I see a 1, 2, 4, and 6. I guess the next 2 givens are 3 and 5. They just left off the numbers. Okay? You would think by the time they got to the 11th edition, they would have cleaned up these errors, but they haven't. So do any of the odds 1 through 5, and then do some of the others 7 through 13. The odds 7 through 13. There we have Sonia pushing her lawnmower again. Good for her. Oh, no, that's not Sonia. She's at 40 degrees. All right, and then there's a 15. I didn't see that one. Oh, and there's more. Next page, any of the odds 17 to 23. Okay? You choose how many of those you feel like you need to go so you understand it. Frankly, I would do some of the easier ones, then jump to some of the harder ones. When you get some that are a little tough, maybe back off a little, and then work your way up. So do that. All right. I don't see this figure in here anywhere. Do you? There it is. That's way over on page 219. So they have no figures for 8.2, 8.3. You get into 8.4. This is sorry PowerPoint. I'm sorry. Okay? So we're going to use poor old, what's her face here, pulling on this thing. She's going to be pulling all day, it looks like. Okay. Let's erase this. Now let's talk about power. Now, in everyday English, we're pretty sloppy when it comes to our language, aren't we?
Yeah.
I've taught a bunch of auto mechanics physical science also, which has physics in it. I swear, they call everything power. You know, the cars are power, their forces are power, work is power, they call everything power. Not in physics. In physics, everything has a very specific meaning. Okay? Now, for those who weren't here, just a little bit of review. One of the first things we talked about was a displacement or a distance, right? And then what's the next operation we did to that? Oh, we got a displacement or distance here. Let's take the time rate of change of moving that distance. And what do we call that? Distance divided by time? Speed or velocity. If it's displacement divided by time, it's velocity. Okay? Because those are vector quantities. Well, once we had a velocity, guess what we decided to do? Take a time rate of change of velocity. What do we call that? Acceleration. All right. My little, why don't you like that? Okay, my gas pedal. Accelerate. Okay? Well, here we've been dealing with energy or work. So what we're going to do now is do a time rate of change of doing work or expending energy. So let's go back to digging in my backyard. Okay, that was so much fun, wasn't it? So I worked for the next, I'd say about 5 or 6 weeks, toiling away, pick, shovel, and wheelbarrow, digging out the patio. Okay? And getting around those rocks. Okay? Well, here came Labor Day. We were starting school right after Labor Day. I was going to have a full load, not going to have all that time on my hand. I'd only got about half the patio dug out. Okay. Now, you might ask yourself, why didn't you have a bobcat come do it in the first place? Oh, you were asking that. Okay. Number one, I'm cheap. But number two, we had the house here. We had a nice pecan tree there. We had azaleas planted. No, we didn't have them planted. We had a big old oak tree here, a maple tree there. There wasn't room to get a bobcat in and maneuver. Okay? But by the time I got about half the patio dug out, actually area-wise it was a little more than half, but we were getting in deeper and deeper soil because it was going uphill. So I had room that a bobcat could get in. So Labor Day weekend was approaching, and we had half the patio dug and no prospect in sight when I was going to, except maybe just on weekends, and that was going to take forever. So we decided to call around and find us a bobcat. And we found one. They came in, and in one afternoon, he dug as much soil as I had dug in 5 weeks. Who did more work? No, we both did the same. Same amount of soil moved, right? Now, in my defense, I hauled it down to where it needed to go. He just piled it up. So, but what was the difference between me and the bobcat? The time it took me to do the work. The time rate of change of doing work. I had, I promise you, way less than half a horsepower, okay? Okay, horses are much stronger than me, okay? So way less than half a horsepower. That bobcat that came in, I'm guarantee you it was probably 200 plus horsepower, okay? Lot more power. So therefore, he did as much work in half a day as I had done in about 5 weeks, okay? So the difference of power. Same amount of work done, but the power much in his favor. So that's what power is. Power is work divided by time. Just like speed is distance divided by time, velocity is displacement divided by time, acceleration is velocity divided by time, power is work divided by time. Okay? Now, what units will we use? What's our unit for work? Let's do SI. Unit for work. Second? Did someone say it? Joule. Okay, not that kind of joule. Okay. Joule and time? Second. A joule per second. Now, what's the unit for power? What's the unit for power? Watt. Yeah, what? Watt. Okay, yeah. It's a watt. And it's a capitalized watt, too. Why? Named after James Watt. Now, actually, Watt didn't define a watt, okay? He defined a horsepower. He defined the U.S., well, back then it was the British system, and he said about the rate at which a standard dray horse would work in a day, that would be a horsepower, okay? So James Watt, he defined horsepower, but then later when they got the SI system, they named the power unit there after him. So let's talk about horsepower then. What's your unit of work in the U.S. customary or British system? Work is, hint is force times distance. Say again? U.S. customary. Force. I stand on the scales.
The weight.
Yeah, same unit as weight. Pound. So that would be pound. And distance? Foot pounds. Okay. So we have a foot pound is our work over second. Okay. Now. Okay. It's, he wanted how much work a standard dray horse. Those are the big hauling horses, you know, like the Clydesdales or something like that. Maybe not quite as pretty. And he said a horse could do about 550 foot-pounds per second. I can't. And that's what he called a horsepower. James Watt defined that. So that's our, now, I don't know why they do this here, but they do. And have we talked about converting units before? How you do that? See, I'm teaching a physical science class, and I'm teaching this class, and I can't remember which I've taught said what to. Here's how I go about converting units. If you wanted to get this in foot-pounds per minute, you're going to need 2 blanks to get it to foot-pounds per minute. Now, and this is a time sign here. The 2 blanks. The first blank is for numbers. The second blank is for units. Always put the units in their place. Then match the numbers with it. Okay, what are we going to? Foot-pounds stays foot-pounds, so there's no change there. We're going from seconds to minutes. So I know what the units are going to be. One's going to be seconds and one's going to be minutes. You have to tell me which one goes where. Always put the units in their place. Which one will go upstairs and which will go downstairs? Say again? Units first. Just think units. Which one? Seconds goes up, absolutely, and minutes go down here. Because the seconds you want to cancel out, and you want minutes under foot-pounds. So yeah, that's where they got to go. Now that you got the units in the place, match the numbers with them. How many seconds in a minute, or how many minutes in a second? Say again? 60 seconds is 1 minute. So we take this and multiply it. The units go out, the seconds go out anyway, and multiply 550 times 60, and that gives us 33,000 foot-pounds per minute. And maybe that's what James Watt actually did. It's a much rounder number than 550. So I'm guessing that's what he did. There's a little blurb over here on the side about this. He was Scottish, did a lot of things. I think he was big on the early steam engines too. He contributed to those as well. All right, then they talk about human horsepower, which I don't want to think about, okay, because I had to dig out the patio. But you can think of that, work through it. We're not going to do it, okay? Let's move on to example 1 on page 209. Going to have to erase this slide because it's as lousy as PowerPoint. Okay. A freight elevator with the operator weighs 5,000 newtons. And they said weighs, so what's that going to be? What symbol? $5,000 newtons. What's that represent? By the way, the middle zero is significant there. They have the bar over that. What is that a measure of? Say again? Someone may have said it. So, work? Is that what I heard?
Sure, yeah, work.
No, it's not work. Newton doesn't measure work. Force, that's your force. And specifically, it's the force due to weight or gravity. I like to call it F sub G, or just call it little w for weight. Capital W is work. It's not work. Okay. So that's your force. Okay. If it is raised to a height of 15 meters, so what's that going to be? 15 meters. And that better be 15.0 meters. It was. Okay. 15.0 meters. What's that going to be a measure of? Displacement. I like to use D. The book uses S. H would work for height. Whatever you want to call it. Do they call it S? They call it S. So we'll call it S. Okay. Now, but it does that in 10 seconds. What's 10 seconds a measure of? That's your time. Okay? What is the power done? How much power is developed? So what's the formula for power? A little louder. I heard. What divided by time?
She's saying watt. Watt.
Okay. It's not watts divided by time. It's work divided by time. Oh, you did? Okay, work. Okay.
Yeah, he was saying say it louder because he couldn't hear.
Okay. It's work divided by time. Okay? Now, we use capital W for watt, but that's a unit. Always, it's going to have a number in front of it. This is a parameter here. That's capital W is work here. But what's your work? What is work? Oh, it was a long time ago, I know. What's work? A little louder. Force times the distance. F times S over T. Now we got all the pieces in place, plug and chug. That's 5,000 newtons force times displacement of 15.0 meters, Newton meter, divided by 10.0 seconds. That is your power. And what will that be? Well, I'm going to be real easy with it and divide 10 into 5,000 and make that 500. 500 times 15. 5 times 15, I think, is 75, isn't it? Yeah. So it'd be 7500. I think. And what would that be? What units? A Newton meter is a what? Joule. Now, joule per second is a? is a what? A watt. A watt. A watt. Okay. So that's a watt. Okay. Or, if we didn't like such big numbers there, what could we call it? Move the decimal 3 places. That represents 1,000. That would be 7.5. Second. You could say times 10 to the third, but if I'm using a prefix, metric prefix, that would be a, what's 1,000? Kilowatt. Exactly. Kilowatts. Okay. 7.5 kilowatts. They just called it 7,500 newtons. Oh, and if I do 7.5, I better do 7.50 because we were supposed to keep 3 significant digits. Had 3 here, and 3 there. So yeah, 7.50 kilowatts. Okay? All right. Let's see if we can get example 2 done. Any questions on that before we move on? Okay. All right, to erase? Yea or nay? Okay? All right. The power expended in lifting an 825-pound girder. 825-pound girder. What's that a measure of? Say again? That is weight, and weight is also a what? Weight is also a force. Force due to gravity. Okay? 825-pound girder to the top of a building 100 feet high. So what's your 100 feet? By the way, they put the second 0 is significant. So what's that a measure of? Displacement, and the book is calling that S. Okay? How much time is... I'm sorry. The power expended in lifting an 825-pound girder to the top of a building 100 feet high is 10.0 horsepower. So your power here is 10.0 horsepower. Okay? How much time is required? So what are we looking for? The unknown here is time. Okay? All right. Now, got a little bit of a problem with units here, don't we? We got pounds and feet. Time, we're probably going to be in seconds. But horsepower, going to have a conversion there. You remember what the conversion for horsepower is? Say again? Thought I heard someone say it. 550 foot-pounds is 1 horsepower, right? So the horsepowers are going to go out, and that will give you 5,500 foot-pounds. Okay? So, how are we going to figure out the time? What is the power formula anyway? No, it's been a long time. Huh? Okay. Power is what divided? Work divided by time. Perfect. Perfect. And what is work? Don't keep asking them. Work is? Work is force times displacement, right? Over time, right? So there's our basic formula we're going to have now. Power is equal to force times displacement over time. Okay? But we want to know what time is. So therefore, I'm going to, this is called a literal equation. That means it's equation strictly in letters, or mostly in letters. Okay? I want time up top. It's on the bottom now. So how I get it up top is to multiply both sides of the equation by time, right? That gets it out of the denominator over there. But now it's mixed up with power, so what will I do to get power on the other side? Divide. So I'll divide both sides by power. Okay? And that gets rid of the power here, so the time is going to be force times displacement over power. Okay, let's see what it is. What's our force? $825 pounds times the displacement. What was it? 100 feet. Right on his foot there. Okay, her foot, sorry. Divided by power, which was, what did we just figure the power was? Say again? Yeah, but we changed that, converted that to 5,500 foot-pounds. Oh, yuck, I messed up. Sorry. Got to get my eraser. Foot-pounds per second. That's what, ooh, I left that off, didn't I? Foot-pounds, I said this wrong. Foot-pounds per second. I left off the per second there. No wonder it messed me up. Horsepower is 550 foot-pounds per second. 1 horsepower. I left off this per second. Okay. Now, notice the pounds are going to go out, and the feet are going to go out. Okay, if they're dressed up nicely. Okay. And you get 1 over second, which is seconds, right? So this will give us units of seconds. So if someone, oh, I'm going to make this much easier. I'm going to divide out my 0 zeros here and just do 825 divided by 55. That saves me punching a lot of buttons. What do you get? Say again? 53? 15. On the nose? 15 seconds. That's how long it's going to take if you have a 10 horsepower device lifting the steel beam. Is that what they got? Let's see. Yep, 15, and they say 0.0 seconds. Okay, we had 3 digits here, 3 digits there, 3 digits there, 3 digits everywhere, so 15.0 seconds. Okay, does that make sense? All right, we got down to, but not past, example 3. So we'll start with example 3 next time, and yes, you need a test. Oh, no, you came in too late. You can't have one. No. Okay, sorry. Did everybody get a test? Sorry about that. All right, that's it. Okay? You have a week to do it. If you can get it done sooner, I'll take it sooner. Okay? But that way, if you do need questions or whatever. All right. So I'm figuring for work and power, we got energy coming up. Okay, we might be able to finish this chapter next time, and if so, I'll try to have a test ready for you then. If we don't, the following week, the following class, we'll definitely have it. Okay? All right, good deal. These mini-term courses sort of fly on you, don't they? So keep them trucking. Good deal. I'll secure the